Good morning, everyone. Today is November the 6th, and some little announcement that there will be a quiz due next week. The quiz material is up to the material for this week. And if you are behind because of test 2, it is time for you to speed up. And I also see that the material for test 3 actually ends at this week 10. Maybe with including a little bit material from test from week 11 regarding inverse function, but the majority of your test 3 basically ends in this week 10. Okay. So what I will cover this week in our discussion, I will go over one old test. You will see that when we go over this this lecture video here, the October the 10th from 2020, the one from this video here, most of the material that I went over there is actually from spring 19 test 3. Okay, from spring 19 test 3, you will be able to see there. So what I will go over today is test 3 from fall 2020. Okay, let me start. Give me a second. To change the view, this will be, I will take from fall 20. Test 3. Fall 20 test 3. Yeah, again, the one from spring 19 test 3 already covered in one of my lecture video, and you can see that also in my notes. Oh, inverse function was covered in 2.7, so I believe already covered. And composition of function, combination of function also covered in 2.6. So yes, we are actually done. This week 10 already covered all the material for test 3. That means you actually have 2 weekends to work on to do well in your test 3. Okay, now let me start. Solution. Part A, find the domain of this function. A rational function has domain or real numbers except the 0 of the denominator. Okay, we need to avoid 3/2 such that the function fx is well defined. Okay, how about inverse function of the function fx? Every time I ask you to do inverse function, I need you to do it in 4 steps, and I even require you to make it into Step 1, step 2, step 3, step 4. Okay, so step 1, you replace the fx by y. Step 2, you swap the x and the y. X becomes y, y becomes x. Step 3, you will solve for y. So I will multiply by the LCD here. Move the move the y terms to one side and the one without y term to the other side. I will factor the y now. So this is y times 2x minus 1 equals to, oh, I'm sorry, this is 3x plus 4. So y is equal to, let me move a bit, in 3x plus 4 over 2x minus 1. Then step 4, the inverse function is 3x plus 4 over 2x minus 1. Now, part C, find the range of the function fx. The range of the function fx is equal to the domain of the inverse function. Domain of inverse function fx. So when you look at the inverse function, you see that the domain is all real number except 1/2. Right? Okay. Now let's go on. Part D, find the G compose F of X. That's G of Fx, which is G of, let's see, what's that? G of X plus 4 over 2x minus 3. You know what? That reminds me of one thing. Instead of me going over this only, let me post the blank test actually on the discussion board. Give me a second. Okay, I already updated my discussion board. I said on the third line here, the third point, that I will go over previous test 3. The part of Spring 19 test 3 is covered in November the 10th video. Okay, so you can see the notes here. Okay, I think it's this one. But I went over that here. I believe I didn't go over all of them. I went over the summary, like the one regarding the polynomials, but I think that's pretty good enough. That's the main topic for that test. Okay, now the blank test for Spring 19 is here. The one I go over today is this. This is the blank file. Okay, now let me go back to the test. Okay, so we were working on part D. G compose F means G of F of X. And what is G, by the way? G is 2x minus 1 over 3x plus 2. So this is 2x minus 1 over 3x plus 2. Now then multiply by the LCD over LCD, multiply by 1, right? That way, then we can simplify the complex fractions. The top left will be 2 times x plus 4. The top right is just 2x minus 3. Don't forget the parentheses. And 3 times x plus 4 plus 2 times 2x minus 3. That will give us 2x plus 8 minus 2x plus 3 big over 3x plus 12 plus 4x minus 6. That is 11 over 7x plus 6. Part E, find the y-intercept of fx. What is y-intercept? Well, that's just f0, right? When x equals to 0, that will be 4 over -3, okay? But we need to express the y-intercept as a coordinate. So y-intercept is 0, -4/3. How about the x-intercept of fx? Now, the rational function is equal to 0 when the numerator equals to 0. Okay, so multiply the left-hand side and right-hand side by the LCD. So you see we have only the numerator, right? Therefore, x equals to -4. With that said, then the x-intercept is -4, 0. Okay. The last part, not the last part, the second from last part. What is the domain of G compose F? We did G compose F earlier. So this is G compose F. So the domain will be all real number except when the denominator equals 0, right? And the denominator equals 0 when the denominator is equals to 0 when x is -6 over 7. But we still have one more thing we need to exclude. We need to exclude the number we excluded from F. The number we excluded from F, we excluded 3/2. Okay, so there are two things that we actually exclude. The one we exclude was the one 7x plus 6 not supposed to be 0. That's from the composite functions, the one from here. Okay, 7x plus 6 cannot be 0. Okay, that's how we get that. We need to avoid -6 over 7. But also, we need to avoid anything avoided in the domain of fx. Okay. So we need to avoid 3/2 also. Okay, 3/2 cannot get into the fx, right? So if it cannot even go into fx, then it won't be going into the composite functions. Okay. Now, finally, part H. What is F compose G compose F? F compose G of F. That's what it means. But we already have this thing. We already have this thing. That's from part D, G compose F, right? Okay, so let me just use that as a chunk. This is F of what is G compose F? 11 over 7x plus 6. Okay. Now F blah is blah plus 4 over 2 blah minus 3. Okay, multiply by the LCD again. That's 7x plus 6, 7x plus 6. That will be 11 plus 4 times 7x plus 6 over 2 times 11 minus 3 times 7x plus 6. That will be 11 plus 28x plus 24. 22 minus 21x minus 18. That is equals to 28x plus 35 big over negative 21x plus 4. Okay, now let me ask you to take a look a little bit. Okay, let me go on. Page 2. We have a polynomial, negative 3 times x plus 4 cubed times x minus 2 squared times x minus 5. Oh, this is a polynomial that already in factored form. Okay, so how do we find the y-intercept? So P0 equals to negative 3 times 4 cubed times negative 2 squared times negative 5. Well, just multiply this all over. What's that? I need to use calculator. That's 3 times 64 times 4 times 5. And that's positive. So that's 3840. There are two negatives to multiply, becomes positive. So the y-intercept is 0, 3840. Remember, x-intercept and y-intercept has to be written in coordinate. Okay, now part B, the x-intercept. The x-intercept, well, we already have the polynomial written in factor form. So it is easy to find the x-intercepts, right? The zeros are, if it is already in factors form, it means the zeros are x equals to negative 4, x equals to 2, and x equals to 5, right? So the x-intercepts are negative 4, 0, 2, 0, 5, 0. Okay. How about the far end's behavior? The leading coefficient is negative 3, right? In fact, what is the degree here? This is degree of 3, degree of 2, degree of invisible 1. So it will be degree of 6. the n is equals to 3 plus 2 plus 1, that's equals to 6. So notation-wise, this is supposed to be a sub 6 here. Okay. Well, anyway, the leading coefficient is negative. The degree is even. So the graph will be like this, approximately. Right? Basically, we usually call that bottom-bottom. So it comes from negative infinity from the left-hand side, and it goes to negative infinity on the right-hand side. Okay, how about the sine graph? Construct the sine graph of px. We use the zeros. The zeros are -4, 2, 5. Those are the critical numbers, right? They are the zeros. And we know that the far end behavior are bottom-bottom. Means in the far right, it will be negative. In the far left, it's also negative. Like you can do testing point also to find this. You can use testing point to find this. Now, if we look back, then we see that the zeros x equals to -4 has odd multiplicity, right? The multiplicity is odd, is 3. So the sign from the left-hand side, the sign on the left-hand side and right-hand side of that critical number -4 will be different. Now, how about the multiplicity at 2? 2 has degree, x minus 2 has exponent 2, which is even. It is even multiplicity, which means the sign does not change. And to confirm, 5 as a 0 has multiplicity of invisible 1, which is odd, means the sign on the left-hand side and right-hand side of the 0, 5 as a 0 will be opposite signs. Okay, now using that, let's sketch the graph. Let's sketch the graph. And we don't need to draw it to scale, but we need to pinpoint the x and the y intercept, important coordinates. Okay, we have -4, 0, 2, 0, and 5, 0. The y-intercept is 0, 3000 something, 3084. So 3840. Okay, and then the far end behavior from -infinity. Now at -4, the multiplicity is 3, right? So when it crosses, it will cross like an x cube. And then at 2, the multiplicity is even. The multiplicity is 2. It means it will bounce. It will not cross. It will bounce like an x square. And at 5, the multiplicity is 1, invisible 1, you see here, right? Which means when it crosses that x-intercept, it will cross linearly. It will just cross like this. Okay. It's not tilting like the one we have around -4 there. Okay, that's approximately the graph. Okay, now don't try to use graphing calculator, because if you try to use graphing calculator, it will look very, very strange. Okay, what you need is to put the x and the y intercept and how the graph behaves at the far end, the very far to the left, very far to the right, how the graph actually behave around the x intercepts. Okay, that's all we want. That's all we want. Okay, if you try to graph that to scale, then this 3840 will be very far to up there, right? Which is not what we try to graph. Okay, that's for number 2. Let's go on with number 3. Number 3, the following functions are 1-to-1. It's so we don't need to check that anymore. find the inverse function of each. Every time we do inverse function, remember, I need you to write it in step 1, step 2, step 3, step 4. Step 1, change the fx becomes y. Next, you swap the x and the y. We did this earlier, right, in number 1. And then step 3, we solve for y. So I add 2 first. And then I do cube root. Now, the nice thing is cube root is one-to-one function. Therefore, when we apply cube root, we don't need to worry about the positive or negative branch. There's no restriction in the domain either. And because the domain of the range for x cubed, the graph of x cubed is this. The range is all real number. The domain is all real numbers. There's no restriction. Okay, so we can just like do cube root and don't need to worry about the domain range. And then I will add 4 to both sides. So cube root of x plus 2 plus 4 equals to y. So the inverse function of x is a cube root of x plus 2 plus 4. Okay. Now let's see part B. Find the inverse function of this rational function. Now, the question already explicitly say this is a one-to-one function, so we don't need to check if it is one-to-one anymore, and that's one. And second, then the inverse is also a function. Okay, the inverse is also a function. So I change the fx becomes y, the same similar procedure. And then I swap the x becomes y, y becomes x. And then I will multiply by the LCD. And distribute. Now the thing is, all the y terms has cube. Actually, that's a good thing though, which means then what we need to do actually to solve for y cube, right? And then after that, we will do the cube root. Now we have the y cube, right? Y cube equals to 6x minus 5 over 4x minus 3. Okay, now then the y will be the cube root of 6x minus 5 over 4x minus 3. Now, finally, step 4, the inverse function is therefore the cube root of 6x minus 5 over 4x minus 3. Okay. Now that's for number 4. I'm sorry. Yeah, I think that's number 4. No, number 3, I guess. Yeah, that's number 3. Number 4 next. Now we deal with polynomial. We have a polynomial, degree of 5, 5, 4, 3, 2, 1. Oh, there's no degree of 1, huh? There's no degree of 1. Okay, be very careful there. Let me help myself. So plus 0x to the 1. Okay, now using the scatter rule of sign, find the possible number of positive zeros. The possible number of positive zeros will depends on the number of times the sign changes, the number of variation of signs. There's no variation of sign. Positive becomes positive, positive becomes negative. One time there, negative becomes negative. There's no change there. Negative becomes positive. There's one change there. It means there are two or nothing. No positive zeros. Why zero, Thomas? Why zero? You have two variation of signs. Why zero? For every number of variation of signs you have, that's the possible number of positive zeros, but also every numbers subtracted by 2 from there. So if, for example, let's say you have 5 variation of signs, right? So either you have 5 positive zeros or only 3 or only 1. Okay, we keep on subtracting by 2 until it becomes 1 or becomes 0. Now let's take a look. How about part B? Use the scatter rule of sign to find possible number of negative real zeros. Now to find the negative real zeros, the number of negative real zeros, I need to replace x by negative x first. I basically reflect this function with respect to the y-axis first. And then simplify. And see how many times the sign changed. One time here, no time here, one time here, another one time here. So there are 3 or 1. Remember, 3 variations of signs. So you start from 3 and then you keep on subtracting by 2. 3 or 1 negative zeros. Part C, use rational zero theorem to determine the possible rational zeros of Px. So the possible rational zeros are plus minus the factor of the constant, either 1 or 2 or 4, from the constant 4. These are the possible zeros. Over the possible, the factors of 9, which is 1, 3, 9, from the leading coefficient. Okay, so the possible rational zeros is plus minus 1, plus minus 2, plus minus 4, plus minus 1/3, plus minus 2/3, plus minus 4/3, plus minus 1/9, plus minus 2/9, plus minus 4/9. Okay. Okay, that's the possible rational zeros. In other words, if we have any rational zeros, like the zeros becomes is a rational number, then it must be one of the number in the list. Okay, it must be one of the number in the list. Now, the next one is the most challenging one, the one that a lot of people really still don't know how to do. Okay, we will try to find the zeros. I will first write down the coefficients. That's 9, and then I forgot. That's the degree of 5, and then 27, -1, -39. 27, -1, -39, And that's negative 39 for degree of 2. Okay, and then degree of 1 is 0, and then plus 4. Okay. The one I will try first is 1. You do this on your scratch paper. You do this on your scratch paper. But I know 1 will be a 0 because when I add the coefficients, the total is 0. If the sum of the coefficients of a polynomial is 0, then 1 is a 0. Okay, now, so what if 1 is 0? If 1 is a 0, then x minus 1 is a factor. So knowing 1 is a 0, right? Knowing 1, so some students like to do this. Oh, what is P1? P1 equals to 0. So what? Okay, so you only know that 1 is a 0, but we don't have any use of that. You just know that 1 is a 0, but then you need to start over to find the other zeros again. Now, no, that's not what we are going to do. We know 1 is a 0. Okay, but so let's try. So when we do try to divide by x minus 1. So 1 is a 0, therefore x minus 1 is a factor, right? Okay. Now, but then we use that x minus 1 as a factor. Basically, our polynomial now becomes x minus 1 times 9x to the 4th plus 36x cubed plus 35x squared minus 4x minus 4. We already reduced that polynomial from degree of 5 becomes degree of 4, which means we have only 4 more zeros to look for. You see what I mean? Okay. So not only 1 is a 0, but we also already reduced the polynomial into 1 degree less. Now, you can try again. If you add the coefficients here, do you still get 0? When I add this, I don't think it is 0. When I add this, it is not 0. Therefore, then I know 1 is no longer another 0. It is just a 0 with multiplicity of 1, but not multiplicity of 2. Okay. Now, let's do more. Let's try more. This is still our scratch work. So let me use, I don't know what else though. Should I try 1/3 maybe? Should I try 1/3? 9. So this is 3. This is 39. This becomes 13. This is 48. Divided by 3 is 16. This is 12 divided by 3. That's, oh, so 3 is a 0. 1/3 is a 0. Oh, that's nice. 1/3 is a 0. Let me use blue color now. I was just guessing 1/3. I was just guessing. So what happened, Thomas, if you guess that and it's not right? Then try other number. Okay, so I tried 1/3. I try 1/3, and it turns out to be a 0. So at this point, my polynomial px is already equals to x minus 1 from the beginning, from this one here, right? Times x minus 1/3. That's the one from here, right? Times 9x cubed plus 39x squared plus 48x plus 12. Now, before I go on, we update our list of possible zeros and rational zeros. Okay. First, the possible zeros on the positive side, there's no variation of sign already here. So there's no more positive zeros. Right? At the beginning in our question A, according to the Descartes' rule of sign, find the possible number of positive real zeros, either 2 or 0. We actually find 2 of them. Those 2 are positive 1 and positive 1/3, right? Now, then when we update our remaining polynomial, we found out there's no more positive zeros. Okay, that's one. So later on, if we try anything else from now on, we will try the negative side. Second, you notice that the coefficients here are all multiple of 3. Let's factor that 3 out. Let's factor that 3 out. So I will get 3 times x minus 1, x minus 1/3, 3x cubed plus 13x squared plus 16x plus 4. Now, then from there we do that synthetic division again. 3, 13, 16, 4. Now, the nice thing is, if we do possible rational zeros, that will be 1, 2, 4 plus minus divided by the factor of 3, 1, 3. No more 9. No more 9. Okay, and the nice thing is we don't have the negative part anymore, right? So either negative 1, negative 2, negative 4, or negative 1/3, negative 2/3, negative 4/3, right? Okay, we only will try these 6 numbers. Okay, going back to our scratch work. So I assume I start from there. Let me try negative 1. Will that work? No, no, negative 1 doesn't work. Negative 1 doesn't work. Even though negative 1 doesn't work, if you take a look here, if we call that our QX, let's say, right? Okay, now notice that Q0 is 4. That's the constant. And according to our computation just now, Q negative 1 is negative 2. Okay, so at 0, the value is 4. At negative 1, the value is negative 2. According to intermediate value theorem, there must be a 0 in between, right? There must be a 0 in between. There must be a 0 in between. So think about what are the rational numbers between 0 and negative 1 in our rational zero theorem. Negative 1/3 or negative 2/3, right? Okay, let's try either one of them. Let's try either one of them. We know this is not right, but even though negative 1 is not a 0, it does give us a glimpse of the possible zeros in between. So let's try, maybe let's try negative 2/3, negative 2/3. This is 3 multiplied by negative 2/3, that's negative 2. That's 11. Oh, this becomes ugly, huh? That's negative 22 over 3. It's too ugly. Let me stop there. Maybe not that one. Let me try negative 1/3. So this is -1, this is 12, this is -4. Yeah, this is the one I think we'll do those. Yeah, so -1/3 is another 0. So at this point, we have Px is equal to 3 times x minus 1, x minus 1/3 times x plus 1/3 times 3x squared plus 12x plus 12. I can factor another 3 out. So multiply by 3, this gives 9, x minus 1/3, x plus 1/3. When I factor 3, I get x squared plus 4x plus 4. Oh, that is a perfect square. So I can just factor it right away. This becomes x plus 2 squared. But we are not done. We are not done. The question is find the zeros and the multiplicity. So the zeros are x equals to 1 with multiplicity of 1, x equals to 1/3 with multiplicity of 1, x equals to -1/3 with multiplicity of 1, and x equals to -2 with multiplicity of 2. Okay, those are the zeros. Then I go on. Write the px in factorized form, which we already did. So I would just copy that. Px equals to 9 times x minus 1, x minus 1/3, x plus 1/3, x plus 2 squared. Okay, now then, how about the y-intercept? The y-intercept is when x equals to 0, p0 is 4. That one is easy. And the x-intercepts are 1, 0, 1/3, 0, -1/3, 0, -2, 0. Okay. That's for part F. Now use synthetic division to find P -3. P -3, we divide the polynomial by x plus 3. So -3 here. Write the coefficients on the top. Don't forget the placeholder for 0x. Okay, let's go on. This is 9, -27, 0, 0, -1, 3, -36. This is +108. This is -324. So this is -320. So P -3 is equal to -320. You know what? I want to box that final answer here. Determine the far end behavior of Px. The degree is 5. The leading coefficient is positive. Is +9. So it will be bottom top. And because the far end behavior is bottom top, it means it covers from -infinity on the very far left and goes up to positive infinity on the far right. Therefore, the range will be all real numbers. Now, not all polynomials have this kind of range. If the polynomial has even degree, then the range will not be all real numbers. Okay, but because the degree is odd, then the range is all real numbers. Now, sketch the graph. Sketch the graph, and we will not sketch it in full. We will just give the one that gives us the x-intercept and the y-intercept. Okay, the x-intercepts are 1 and 1/3. Let me put 1 here, 1/3 here, and I don't draw it to scale. The y-intercept is 0,4. The x-intercept again, -1/3. This is 1/3 here. This is 1, -1/3, and -2 with multiplicity of 2. Okay, we know it comes from far bottom left. -2 is a 0 with multiplicity of 2, so it bounds. -3 is a 0 with multiplicity of 1, so it will cross that linearly. 4 is the y-intercept going down, and 1/3 is a 0 with multiplicity of 1, and 1 is a multiplicity of 1 also. Okay, that's it. That's what we need. That's what I want to see the behavior on. Now, do not use graphing calculator because graphing calculator will not give you a good result. Okay. One of the weakness of graphing calculator is it will give you the graph to scale. And once the graph is to scale, then either the graph will look very skinny or the graph will look very, like basically not really feasible. And you will not see all the important ingredients at once. Okay, not a good idea. Let me go on with page 4, number 4. We have this polynomial degree of 7. Oh, wow. Oh, hold on, but the degree seems to be a nice one. It's degree of 7, degree of 5, degree of 3, and degree of 1. It's all odd, huh? So I think later on we will see that this polynomial here is an odd function. Okay, let's see how many positive zeros are changed one time, another one time, another one time. So 1, 2, 3. So there's 3 or 1 positive zeros. How about the negative zeros? Replace the x by -x. This is what you will get. And we have 1, 2, 3 positive zeros also. So 3 or 1, I'm sorry, 3 variation of signs, so 3 or 1 negative zeros. Okay, now, but I hope you noticed that if we factor the negative here, if we factor the negative from this polynomial, we will get negative of x to the 7 minus 16x to the 5th minus plus 75x cubed minus 108x. Is it right? Which is negative px. In other words, then this px is an odd function. It is symmetric with respect to the origin. So let's say the function is something looks like this. Then on the left-hand side, it will look like this. It's symmetric with respect to origin. Now, with that said, it means then whatever zeros we have on the positive side we also have the zeros on the left-hand side, right? Okay. Now, let's come back here. Let me erase that. So for those who don't watch the videos, will not understand what I do. Okay. Find the rational zero theorems. Okay, I will factor the x out first. It has common factor x. So x times x to the 6 minus 16x to the 4th plus 75x squared minus 108. So according to rational zero theorem, the possible rational zeros are, actually 0 is one of them for sure, right? 0 plus minus the factor of 108, 1, 2, 3, 4, 5, 6. Uh-oh, that's a lot, huh? Is 8? No, 8 is not. 7 is not. 9 is. 9 is, so divide by 9. 108 divided by 9, that's 12. So after 9 is 12. And then 6, 18, 25, 27 times 4. That would be 36 times 3, 54 times 2, and 108 over 1. So the possible rational zeros are 0 first, and then plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 9, plus minus 12, plus minus 18, plus minus 27, plus minus 36, plus minus 52, actually 54, not 52. 54 plus minus 108. Oh, that's a lot, huh? That's a lot. But the nice thing is we already factor x out. So we are only dealing with, so 0 is a 0, right? From here. We only deal with x to the 6 minus 16x to the 4 plus 75x squared minus 108. Okay. Now, let's check. Is 1 a 0? Is 1 a 0? We add the coefficients. 1 minus 16 plus 75 minus 108. 1 is not a 0. When we add the coefficients there, it turns out it is not equal to 0. So 1 is not a 0. Let's try 2 then. Okay. Now, this is our scratch work, right? Let's try. I use green for my scratch work. 1x to the 5th, 0x to the 5th, negative 16x to the 4th, 0x to the 3rd, 75x squared, 0x, negative 108. Let's try to divide by x minus 2. This is positive 17. It's not, huh? Or positive here. Positive here. Oh, it's not. So 2 is not a 0. Okay. Change. Instead of just keep on staring at that and wonder if it works or not, how about you trying it? Okay. So 1 doesn't work, 2 doesn't work. Let's try 3 or 4. Okay, let's try 3. 1, 3, 3, 9, negative 7, negative 21, negative 63. What's that? That's 12. 2, 6. Oh, so 3 is a 0. 3 is a 0. Nice. Okay, let me change it. That's my scratch word. Let me change it into my correct word, the one I will write on the paper. So a lot of scratch work needed here. Okay, 1, 0, negative 16, 0, 75, 0, negative 108. And I tried 3 earlier. Did I try 3? Yeah, I think I tried 3 and it does work. Now remember that this function is, this polynomial is odd functions. It means if 3 is a 0, therefore negative 3 must be also a 0. You see that? Okay, 3 is a 0, therefore negative 3 is a 0. Remember 2 was not a 0. 2 was not a 0. Because 2 was not a 0, then negative 2 was not a 0. At this point, we can actually update our rational zero theorem. That's factor of 12 over factor of leading coefficient 1. Right? But we already tried the 1 didn't work, 2 didn't work. Will 3 still work? Will 3 still work? I don't know. I don't know. I really don't have any idea. I don't think 3 works. Will 2 work? I really somehow I thought 2 works. Let's check again. Let's check again. Will 2 work? Yeah, 2 works. Did I try 2 earlier? Does it work? It's supposed to work earlier. You know what? Let me do it again. 1, 0, negative 16, 0, 75, 0, 108. We tried 2 earlier, as I remember. Oh, I think I made a mistake there. So this is 27 supposed to be. Yeah, I make mistake in my computation. But 2 works. I thought 2 didn't work. I was too fast with my computation earlier. Yeah, 2 works. Let me erase this. That was my scratch work. I change it to blue now, which is the one I write, which means that's the one I write on my my test paper. Because 2 works and this is an odd function, then negative 2 also works. Now the last part here means x squared minus 3 equals to 0. So x squared equals to 3. And x is plus minus radical 3. So the zeros are x equals to 3, x equals to negative 3, x equals to 2, x equals to negative 2, x equals to radical 3, x equals to negative radical 3. So far, we have only 6 zeros with multiplicity of 1. The degree is degree of 7. So we are missing 1 0. What are they? What's that? The very first one we didn't write x equals to 0. Remember when you factor that 0 out? It means x equals 0 is a 0. Okay. Now all of them with multiplicity of 1. All of them with multiplicity of 1. Okay, now then we go on. Write fx in factored form. So is it fx or px? Yeah, px. Oh, fx. Px is x times x minus 3, x plus 3, x minus 2, x plus 2, x minus radical 3, x plus radical 3. Find the y-intercept. The y-intercept is, of course, when x equals to 0, the y is 0. The x-intercept will be 0, 0, 3, 0, negative 3, 0, 2, 0, negative 2, 0, radical 3, 0, negative radical 3, 0. Synthetic division divided by x plus 1 means this guy is negative 1. Degree of 7, 6, 5, 4, 3, 2, 1, constant. Okay, so don't forget the last 0. Don't forget this one, the last 0. Okay, so 1, negative 1, negative 1, 1, negative 15, 15, negative 15. This is 60, negative 60, negative 60. That's 60, 168, negative 168, negative 168. So P, oh, no. So the quotient Px divided by x plus 1 is the degree of 7 becomes the degree of 6. X to the 6 minus x to the 5th minus 15x to the 4th plus 15x to the 4th. I'm sorry, to the 3rd. Plus 60x squared minus 60x plus 168 minus 168 over x plus 1. Part H, what is the far end's behavior? The leading coefficient is positive 1. And the degree is 7. So that will be like this, right? So that will be bottom top. In fact, you can say that the range is also still all real numbers. Okay, how about the sketch of the graph? Label x-intercept and the multiplicity of each and the y-intercept. The y-intercept is 0, 0. X-intercepts are 2, 0, negative 2, 0. 3, 0, negative 3, 0. Actually, one more, radical 3. Radical 3 is less than 2. So radical 3, 0 and negative radical 3, 0. Okay, those are the x-intercepts. Now the function, all the zeros are all multiplicity of 1, and it is an odd function. So from bottom left, go up here, 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 here. Okay. That's for this question. Let's go on. That's page 4. Let's see page 5. Oh, only one question here. Find the inverse function for this function where x is less than equals to negative 3. This is a quadratic function, which is not one-to-one. Quadratic is not one-to-one. But with this restriction, when x is less than negative 3, it may becomes one-to-one. Okay, it may becomes one-to-one. Let's take a look. Let's take a look. Let's take a look. Let's take a look. So step 1, y equals to x squared minus 6x plus 4. Step 2. Actually, if we can make this into completed square, that would be better. You know, it's like this is equal to, that's just another method. That's just another method. So let me do that other method first. Y equals to x squared minus 6x plus 4, where the x is less than equals to 3. Okay. I will complete the square. So y equals to x squared minus 6x plus 9 minus 9 plus 4. That's for x at most 3. Okay, so I add 9 to complete the square, but I subtract by 9 to compensate that. So my y is equals to x minus 3 squared minus 5 for x is less than equals to 3. Okay, so if you think about it, the graph is has vertex at 3, negative 5, but you only have the left branch. Supposed to look like this, right? But you take only the branch on the left. Now, but you see, if you take only the branch on the left-hand side, then the graph becomes one-to-one. Okay, so when I swap the x becomes y, y becomes x, then the x here becomes y, right? And so for y, x plus 5 equals to y minus 3 squared, where the y is less than equals to 3. When I do the square root, then becomes plus minus square root of x plus 5 equals to y minus 3. Okay, so 3 plus minus square root of x plus 5 equals to y. But don't forget the y has to be less than equals to 3, right? That implies we can only take the negative branch, because this 3 plus something positive will be more than 3, right? For the y. No, that's not what we want. So put things together, we get y equals to 3 minus, not the plus part, minus square root of x plus 5. That's our fourth step. That's our fourth step. F inverse x equals to 3 minus square root of x plus 5. Now, don't forget, once a function is one-to-one, therefore we can find the inverse function, then the inverse function has to be one-to-one also. Okay, the inverse has to be a function and it has to be one-to-one. Okay, now notice that if I do not use this restriction, here, if you get rid of this, then you will be stuck with the plus minus, right? You will be stuck with the plus minus. Okay, now once you're stuck with the plus minus there, then you cannot write that as an inverse function. I mean, you get the inverse, but that's not a function. Okay, that's why that restriction becomes necessary. Okay. Now, suppose we try to do it with regular way. So let me move this a bit to the left so that I have enough space. X is less than equals to 3. When I swap X becomes Y, Y becomes X. Okay, then I will solve for Y, right? So I set one side becomes 0. And then from there, I will use quadratic formula. I can use quadratic formula. I can also use completing the square, but let me use quadratic formula. Y equals to negative b plus minus square root of b squared minus 4ac over 2a for y to be less than or equals to negative 3. So 6 plus minus square root of 36 minus 16 plus 4x over 2, where the y has to be less than or equals to negative 3. Y equals to 6 plus minus square root of 20 plus 4x over 2, where the y is less than or equals to 3. I can factor 4 from inside the square root. That square root of 4 is 2. Now I can factor 2 so I get y equals to, the 2 cancels, 3 plus minus square root of 5 plus x, where the y is at most 3. But if the y is at most 3, then y is 3 minus square root of 5 plus x, right? No other way. We cannot take the positive branch. Finally, then f inverse x is 3 minus square root of 5 plus x. Basically the same answer with what we have there. Okay. Okay, that's for these solutions. Let me write down. This is from fall 20. Fall 20, Math 245, Test 3 solution. Okay, that's where I will stop. I will post this solution in our discussion board.